Hello everyone. In this video, we are going to talk about the simplest semiconductor, which is a diode. Diode is basically something that allows the current to flow in one direction, but not in the other direction. In mechanical systems, this is similar to a check valve. Okay, so it's a one-way street, basically. That's what it is. And that is very important because sometimes you really do not want the flow to go backward in the circuit, and that's where diodes comes into existence. So they're typically made of material like silicon or germanium, and they have two legs or two sides. One side is the positive side called anode, and the other side is the negative side called cathode. And you can see the symbol for a diode is, as you can see, it's like an arrow which shows the direction of flow. So the flow goes this way, but not the other way around. And if you look at an actual diode like this, you see that on one side they have a band. They have a white band, and the white band is always the cathode side. So that's the direction that the current is flowing, is from the side that doesn't have the white band to the side that does have the white band. And you can see that over here as well. Okay, so that is a typical diode, but diodes have lots of different shapes, lots of different applications, and so on, and we're going to get to that. So when the anode is connected to a higher voltage than cathode, then, as I said, the electricity will flow. That is what we call forward bias. Now, the difference between the voltage on anode and cathode should be some specific amount. It's not like just a little bit more than zero, like 0.001 volt allows the flow. There should be a threshold, and we're going to talk about it. That's the voltage of anode is bigger than the cathode, then the voltage will flow. And in the opposite direction, it tries to stop it, and that is when the voltage of cathode is bigger than anode. That is called reverse bias, and the diode will typically block the current, so it goes like an open circuit. And of course, it can only resist up to so much. When the difference of voltage of cathode and anode becomes so much, then you can also go in backward direction. And there are diodes that are only doing actually reverse bias, like Zener, and we're going to talk about that. So how would you create a diode in the first place? Well, I don't want to get into a lot of details about that, but the basic diode is what we call a PN junction diode. That is the most common diode that you see, and PN is positive and negative. So what you do is you take some semiconductor, like, as I said, silicon or germanium, and on one side of this, you are going to, we call, negatively dope it. What is that? So you're adding chemical elements like phosphorus or arsenic that have extra electrons. And so this side will have extra electrons to it, okay? The conducting electrons. And so that is called negatively dope. Again, I don't want to get into valence electrons and all those chemistry things, okay? But if you want, you can dig more deeper into this area. And then the other side, you make it positively doped. So here you add chemicals like boron or gallium, and make the other side to have excess of holes or missing electrons. So you make one side to have more kind of free electrons, the other side to have more of basically holes or lacking electrons, and then you attach these two negatively and positively doped segments together to make a PN junction diode. Now, when you put them together, what will happen? So if I want to show you with the pictures, and these pictures are taken from this website, by the way, so wherever I borrowed anything from anybody, I made sure to mention it, okay? So these pictures are taken from this website, and then when we go down there, I have some of these plots and everything, correct? So I will add all of the references, and you know that the main book that I'm using is from our main textbook here, which is Introduction to Mechatronics by Carrier et al. So just keep that in mind. So what happens when you put P and N together? So on the P type, remember you have excess holes. On the N type, you have excess electrons. So in this region, from here to here, in this region, the electrons start flowing to the left side, right? So these electrons start going here. And on this side, the holes on the P side, the holes start flowing to this side. And when the electrons flow to the left side, behind them, they would leave immobile or stationary positive ions. That's why you see all of these positive ions here on the right side. And on the left side, where the hole moved to the right, they leave behind these immobile or fixed negative ions. Okay? And in between this, right at the boundary, you also have a region that literally does not have too much of charge, because in that region, so it's a small band here in between that is basically free of any charge, okay, very narrow band. So what you have is now a region that has kind of an electric potential or a voltage between them, right? Because you have some positive total charge on this side and negative on this side. And this region, all it has is immobile ions. So it does not have any holes or electrons, anything that can carry charges, whether positive or negative. And this region that has only immobile ions, we call it depletion region. And inside this region, as you can see, there is some electric potential. Okay, and of course, there is some voltage here, which we call barrier voltage. Good. So this is what happens when you put them together. Now, when you forward or back or reverse bias a PN diode, what's going to happen? So the top picture here is the forward bias. So this is the P side, this is the N side. So that's your anode, this is your cathode, and your basically diode is like this, correct? So you see that you connected the positive side of the diode to the positive side of the battery, the negative side of it to the negative side of the battery. In this case, the electric field or the potential that you have due to the battery is on the diode is from right to left. So that is this field 1. And if you remember, in this case, if you compare this one with this one, I basically reversed the direction of N and P. Here, the N is on the right, P is on the left. Here is backwards. So the charges are going to be positive on this side, negative inside the ions, right? This is the positive, this is the negative. So the electric field built in to the PN is going to be in this direction, from positive to negative. It's going to be in direction 2. So you see in the forward bias, the electric field of battery and the diode are in the opposite direction of each other. So what happens? When one becomes strong to overcome 2, that is when the electrons, or in this case, the positive charge, can flow in this direction, or it can say the negative charge flows in this direction. Okay, and this is when 1 is bigger than 2. Field 1 is bigger than field 2, or voltage 1 is bigger than voltage 2. Now, how much is voltage 1 or voltage 2? Well, voltage 1 has to be bigger than 2. 2 depends on the type of material that you use for making the diode. Is it made of silicon or is it made of germanium? So there are different built-in voltages or barrier voltages in them. And typically, if you want numbers, I have some numbers for you. So for silicon diodes, it's about 0.7 volts, and for germanium, it's about 0.3 volts. Okay, so once you pass 0.3 for germanium and 0.7 for silicon, that is where you can conduct electricity. Now, on the reverse bias, that's where you connect the positive of the battery to the N, because this time, again, if you look at it, your diode is the same as last time. So you have this diode, and this is the positive, this is the negative. So you see negative of diode connect to positive of the battery, and positive of diode connected to negative of the battery. In this case, remember, electric field is basically for the battery is in the direction of in the direction of positive to negative, okay? And the built-in is also from positive charge to negative charge. So in this case, 2 was already to the right, and 1 in this case is also going to be to the right. So you see, your battery voltage will basically reinforce the built-in voltage, and it would never cancel and overcome that. It makes it even stronger. So there is no way for your positive charge to pass through this. Why? Because this positive charge is going to be repelled by these positive charges. Or if you say negative charge, the negative charge will be repelled by these negative charges, and it gets stronger and you do not pass. Okay? So, and you see, in reverse bias, the current is not going to go through. In forward bias, as soon as the battery voltage is bigger than the built-in voltage, you are going to have basically current flowing. So this is the basic of PN junction. Now, if you want to get these numbers, remember I said 0.3 and 0.7, you can use a multimeter and you can check the number, okay? So if you connect the positive or the anode side of the diode to the V part, or the positive part, and the cathode part to the COM, or to the negative in this case, then the negative to the COM, right? So the negative of diode to the COM, the positive to the V. This should be allowing you to get the voltage and read the built-in voltage. Okay, to show you that in practice, so here is a diode, okay, that I have. And this is my multimeter, and you can see that I put it here on the diode, and then you have to click on the function, so it shows the diode symbol, as you can see over there. And then, as I said, now you have to connect. Okay, so here we go. The COM port is attached to the cathode, and the V is connected to a node, and you can see the number 0.558, or about 56 volts. Okay, so this is most probably a silicon one, but it has a smaller typical barrier voltage than the ones that have 0.7. So this is what you can read through a typical PN diode. Okay, now that we learned some very basics about diodes, let's go ahead and look into more depth into formulas, into graphs, and so on. So a PN diode, when you put it in forward bias, and when your voltage is bigger than the barrier voltage, okay, then, as I said, there will be some current through the diode, right? What relation here exists between the current going through the diode and the voltage that you applied to the diode, okay? The equation is what we call the Shockley diode equation. This equation here that you can see. And it says that the current is equal to, the current through diode is equal to some very small current. We call it the reverse saturation current, IS, which you can read from a typical diode data sheet. And then times some exponential term minus 1. This exponential term has the voltage that you applied to the diode from the battery. Okay, and VD is divided by NVT. What is N? N is what we call an ideality factor, which is a number between 1 to 2. Again, it can be found in the data sheet of the diode. And VT is what we call a thermal voltage, which for most of the cases is about 25 millivolts. So the behavior is exponential with V versus I. So if you plot V versus I, or in this case I versus V, so this is VD and this is ID, you see that the behavior is exponential. But as long as your voltage is bigger than some initial voltage of 0.6 or 0.4 or 0.5, whatever it is, so once you pass that, now you get some exponential behavior in this region, which is called the forward bias. Okay, so literally after VF, your diode does not show much of a resistance. It literally shows like 0 ohm resistance. If you do it on the multimeter, it does not show much of a resistance, okay, because it allows the flow. It just resists up to 0.6 volts or 0.3 or 0.5 or anything that we have. So this is in forward bias. We go with the Shockley diode equation. Now in the reverse bias, all you have is just the IS current. That's what we call the reverse saturation current, which is basically a leakage, a very small leakage current. Okay, and you can see that here. So in the reverse direction, you only get very, very small current, which is basically negligible. In the forward, first 0, then exponential. And this reverse, in the reverse bias, this small current only flows up to so much of voltage. Once you reach a voltage which is called the Zener voltage or the reverse voltage, or you might call it breakdown voltage, that's when the behavior is going to be different. So for now, we only look at this region in the forward and reverse bias. After that, as I said, after this point, you're going to see that the behavior from this point onward to the left is going to be different, and we're going to discuss that separately. But this is kind of the current voltage behavior that you see from a PN diode. Okay? So before I move on, I wanted to show you another equation that you might see here and there. Instead of this equation, you might see this one. That is the same equation, okay? Except now, instead of this VT, this thermal voltage, they have this guy here, KT over Q, which you can see the KT here and the Q is gone to the numerator. Okay, that is the same as VT, the thermal voltage, where here K is the Boltzmann constant, which is 1.38, 10 to the negative 23 joules per Kelvin. And Q is the electron charge, which is 1.6 times 10 to the 19 Coulomb. Okay, so, and T is the absolute temperature. So at 300 Kelvin, which is about the room temperature, this number, as I said, is about 25.85 millivolts, which is what you can see over here. So that VT depends on the absolute temperature. If you calculate it at a different, if the operating condition is a different temperature, you can plug in a different temperature here and get your VT. Okay, so the VT part of it, or KT over Q part of it, is fixed, right? Only changes with temperature. This N is something, as I said, we can find from data sheets, and this IS, okay, the reverse current and the ideality factor. And I'll show you right now in a data sheet. So here is a data sheet that I found from the internet, and these are on this basically 1N 4001, 4002, 4000 series basically. So in these guys, these rectifier diodes, there are some numbers, and the one that you want to see right away is the reverse current, this guy here. That is what you need. Okay, that is your IS. And you see that it depends on the temperature. At room temperature, it's about 5 microamps, as I said, very small. But if the temperature goes up, it can go up to 50 microamps. It's still very, very small in the reverse direction. It's basically like blocking it. It's kind of like noise, 5 microamps. But you see that it does depend a little bit on the temperature. So in this here, it's not called I of S, it's called IRM, but that's the same as IS in this here. Okay, and then you don't see 8N here, the ideality factor. So for that, you can go and look at one voltage and one current here, and you see that you have basically the average forward rectified current is about 1 and the forward voltage is 1 as well. So if you go back and into this formula, plug in the numbers, right? So come back here and plug in a 5 microamp here, and then here 1 amp, and here 1 volt, and this VT is that 2585 microvolt. The only thing unknown is N here. Okay, you can find anything else. So if I solve for N, in this case, I get 1.86. And as I said, it's typically between 1 and 2. So you see the ideality factor of this is basically 1.86. In ideal ones, this is a 1. Okay, but if it's not ideal, that's between 1 and 2. And for this one, it's 1.86. So here I showed you how to find the important data from a diode. What you need is the reverse current if you need it, and then you can find N. But another extremely important thing is this guy that you need to pay attention to. That is this one, reverse voltage, or if you want, you can look at, that's RMS. You can look at the maximum one or the peak one here. Okay, this one or this one. Look at them. These are extremely important. This is up to the voltage that the diode will resist the direction in the backward bias. Up to how much voltage can you apply and still it withstand and blocks the current. You can see that depending on the type of the diode, you see that number is about 50 for this one. For this one is 100, 200. So if you want to block more voltages up to 1,000, you have to pick the type of diode that you want. Okay, so that reverse voltage is another extremely important thing that you need to pay attention to. Now, there are other things too, thermal resistance, there is capacitance and so on, but they are not as critical. The other thing that might be very critical is basically the operation range for temperature. So you see in Celsius, you can only work with this guy from -65 to +125. If you're working outside this range, do not use any of these diodes. They will fail. They will break under those heat, extreme heat or extreme cold. So these are important critical numbers that you should expect to see in datasheet of a diode. Okay, so we talked about it and we said they act like a check valve and they only block current in one direction. They allow it in the other as long as your voltage is past their barrier voltage. Now, where would you use them? One major application of these diodes, as I said, and you just saw, it's a rectifiers. Rectifier means what? Means converting AC voltage to DC voltage. A current that is constantly changing harmonic to a voltage that is almost constant. Okay, and you use this anywhere that power AC generated needs to go to DC and run the system. In Tesla cars, electric cars, these rectifiers is everything. Okay, they are very important. So how do they work? One mechanism for it is called a full wave rectifier, which is basically 4 diodes form like this. Diode 1, 2, 3, 4. You see, 1 and 4 are in one direction and 2 and 3 are kind of like parallel in the other direction, and they are connected. And also you might have a resistance and capacitance if you want it to go smooth like that. If you get rid of those, you're going to get only rectified in terms of half sine waves. But if you want it to almost go constant, you definitely need the capacitor to kind of damp it down. So how does it work? So in the positive cycle, in the positive part of the sine wave for AC, what happens? This side is positive, this side is negative. And remember that in diodes, you only go in the direction of the arrow. So when the positive voltage come here, okay, what happens? Well, this arrow is available, this D1. So it is going to go pass through D1. It comes here. This one is blocked. That one is blocked. So it has to go like this, goes through that load, comes back, comes here. When it reaches here, again, this branch is a dead end. So it has to go through here. And then it goes like that. And that is the path that you can see. Okay. So it goes like that. And if you look at the direction that the voltage is going through the load is from top to bottom like that. Good. Now in the negative cycles of AC current, the top part becomes negative, the bottom part becomes positive. So the current, if it goes like this, comes here to this junction. Again, here, this one is dead, this one is, so that one is dead, so you go through here, you come to this junction, again, this one is dead, you go through here, you go through load, come back here, come here, again, this one is open, so you go like that, come back and go. And again, if you look at the direction of this arrow for the load, you see, again, it's top to bottom. So although here the direction of the voltage for this supply is changed, it's in the opposite direction, but for the load, it did not make any change. In both cases, for it, it's top to bottom, or positive is here, negative is here. So you can say the load basically fills it like 4 half sine waves, but all in the same direction. So now you don't go positive, negative, you go all positive. So this is kind of rectified in sense that the sign of the wave does not change, the sign of the voltage does not change. But again, if you wanted to make it kind of constant as opposed to this kind of wave, which is kind of more like a PWM as opposed to this one, then you need to bring a capacitor and a resistor and make it a low-pass filter. And in low-pass filter, what happens is, let me show you. So this is that signal that comes out of these diodes. Now, when it goes to the RC circuit, during this portion here that the voltage is increasing, the capacitor starts charging. And you see the output voltage is the voltage across the capacitor. So it starts charging, charging, charging up to here. Then what? Then when the voltage from the supply here, this Vs, and let's call this Vc, when you start going down here, what happens? Your Vc is fully charged, so let's say 5 volts, for instance, or 10 volts or whatever. So this is 5, your Vc is now at 5. Your Vs came from 0 to 5, it charged it. Now when Vs goes down, so let's say it goes below 5 volts, and your Vc is 5 volts, now Vc is starting to discharge, right? Because now your Vc is bigger than Vs, so the charge starts to go back and starts discharging, okay? So your voltage starts going down a little bit, as you can see, right? So it starts discharging, but what happens? When your capacitor starts discharging here, your source voltage goes down, so you keep discharging, comes up here, and then right here, which you can see there, that is where your capacitor voltage come down to this number, whatever it is, let's say 4 volts, and your Vs also came back from 0 to 4 volts. So here your Vc is, let's say, 4 volts, and your power supply is also 4 volts. At that point, since they both have the same voltage, capacitor starts discharging and it stays at 4, but Vs keeps going up from 4 to 5. And for this portion, let me use a different color. For this portion where you go green, this is again, your Vs is bigger than the capacitor, which is a little bit discharged. So again, your power supply starts charging the capacitor, so you see it goes up a little bit. And then again, Vs starts dropping, capacitor is fully charged, so it starts discharging again. And then again, Vs comes back, reaches the voltage of kind of a little bit discharged capacitor, keep charging it, and you get these ripples. But if you do that very fast and the time constant of the system is not very small and it kind of matches this frequency to a little bit, you get this kind of almost constant voltage with a little bit ripple, and this is your DC voltage, this is your input AC voltage. So that is your rectifier. We call it full wave. Why full wave? Because it acts both in the positive side of the wave and in the negative side of the wave. So this is called a full wave rectifier that you see one of the major applications of diodes. Now, remember I said one thing. I said that diodes work in the forward bias, but there is a specific type of diode that is called Zener diode. These guys are actually designed to work in the reverse bias. These are kind of backwards compared to the other ones. Why? What happens to these guys? Remember, I said up to so much voltage, the diode will resist in the reverse bias, up to so much, which we call it Zener diode or breakdown voltage. Up to so much, it is going to resist. Good? What happens after that? After that, it kind of surrenders completely, gives up, and allows the voltage to fully pass and shows literally zero resistance. So if you look at the voltage current behavior at the Zener, you see that it kind of boom goes like that. And you see your current starts increasing without any more increase in the voltage that you need to apply. So you can say that when voltage is bigger than the Zener voltage in the reverse direction, your resistance becomes literally zero, and you are going to be fully conducting in the reverse direction, which is this region here. Okay? So this is a Zener diode. Now, what is good about it? What's so important? Why would you want to run a diode in the reverse bias more than so much voltage? Remember, the data sheet showed 100, 200, 1000 voltage. What's the use of that? Well, one application is because in the reverse region, as you just saw in the reverse, the Zener diode keeps an almost constant voltage. Look at that here. If you look at this graph, you see here, it's almost like a vertical line. So I can say that the V of the diode is almost what? Is almost constant. The voltage across the diode does not need to change for the current to go. So it maintains an almost constant voltage, although the current is flowing through that. Well, what's the good thing about this? Well, if you combine it with the resistor, guess what you can get? You get the important component that you have seen a lot here and there, and that is called a voltage regulator. These are the components in electric circuits that keep your voltage at the same level, even if the current that your load is demanding changes. Even if this I1 is changing, it is going to keep this voltage for you constant. Okay, and that is called the voltage regulator. So you probably have seen this. I said, let me add a picture. You probably have seen these components, right, that look kind of like the transistors. And these are, with these three legs, these are your voltage regulators. Now, in one of my future videos, I'm gonna make circuits with this and I'm gonna show you. But these are very important in holding the supply voltage constant, especially when you are doing some charging or in many electronics, in computers, laptops, phones, and so on, in EV cars, in lots of places. Especially, as I said, for charging stations, for anywhere that needs a constant logic voltage, let's say 5 volts. In many electric circuits, use a voltage regulator of 5 volts to make sure that your logic is working and it is receiving the 5 volts regardless of how much load is demanding for the current and so on. So the voltage regulator is typically made of diodes and Zener diodes. Now, one thing I want you to pay attention to is the symbol of a Zener diode is like that. So it's not like a straight line and the triangle. It's basically this kind of broken line. And if you look at it, the way that the voltage is applied is in the reverse direction. Remember, for a diode, if it was like this, you should have applied the positive here and the negative here to flow in this direction. But for the Zener, it is in backward direction to operate. So you see it is in reverse bias that it is connected. Okay, so that is a Zener diode. And one thing before I go to the next group is just for these full wave rectifiers, you might see something like this. So if you see something like that, that is a basically chip, that is a component, electric component for a full wave rectifier. So if you see something like that, that is a full wave rectifier. I'm just trying to show you pictures of them as well. You see a diode, if you see a voltage regulator, I want you to see them and know how they look like. So when you want to use them in mechatronics project, just taking a look at them, you know what kind of component you are dealing with. Okay, the next group of diodes is called the Shockley diode. Okay, and what is a Schottky diode? So remember the way that we made the PN junction diodes, we had semiconductors like silicon or germanium, doped positive, negative combined together. But in Schottky, what we do, we create a junction between a semiconductor and a metal. Okay, and when you add metal to the semiconductor, they have some advantages or characteristics compared to the PN ones. What is it? First of all, their forward voltage, the voltage you have to overcome to go in forward bias, is less than silicon ones. It's typically between 0.3 and 0.4. It's not like 0.5, 6, 7. It's a little bit, when I say significantly, it's not like zero, but it's less. So maybe significantly less is not super meaningful, but they are smaller. They are closer to germanium. And that's not their only property, because if you remember, or if you know, the cost of germanium diodes is more than silicon ones. These Schottkys are even a little bit more expensive than typically germanium ones, not just because of this forward voltage, but the better thing they have is the faster switching between conducting and blocking. Okay, so their time that it takes them to go from conducting or forward mode to blocking or reverse mode is literally very, very small. Typically, there is some time when your diode goes from forward bias to reverse bias. There is a little bit time between them that happens, which we call it a recovery period. Okay, so it's not instantaneous. There is a little bit time, but these guys, their recovery time is essentially almost zero. Again, not perfectly zero, but much smaller. So if you have applications that needs very fast switching between forward and backward bias or conducting and blocking, you need to use a Schottky diode because they are acting much faster. And if you want to look at the picture of a Schottky diode, their picture is very similar to the common PN diodes, okay? But their symbol is different. So this is the PN diode, this is the Zener. By the way, that's the appearance of a Zener that you might see. And the Schottky, their symbol is kind of like this. So this kind of broken line is showing something like a backward integral or a backward S. So you see, they are still working in forward mode, but if you see that symbol, that is the symbol of Schottky. And as I said, their application is fast switching. So they are used in high frequency rectifiers and power supplies. Okay, if the frequency is high, if the switching is fast, use them over there. And this is one sample, basically chip or electronic for a Schottky diode. For Zener diode, this is typically one typical one. And as I said, they are good for over voltage protection and voltage regulators. PN ones, they are used in rectifiers, in clippers, and so on. And this is one common one, N4007. Okay, so these are the three diodes that so far we have discussed. Okay, what else do we have? I want to talk about two other diodes. One of them is the one that you know, light emitting diodes or LEDs. That are the very common diode that you use on lots of applications, indicators, and so on. And finally, we have a photodiode. Okay. So two other categories that we want to discuss and look at their voltage current behaviors. So some semiconductor diodes made of special material like gallium, if you apply voltage, forward bias, forward voltage to them, they emit light. Okay? They emit light, so we call them light emitting diodes or LEDs, which here I guess you can see in this picture, right, in this video. So this is a red one, and here you see I have a collection of different colors. There are blue, green, white, and there are these guys that you see on the right side. I made a video on them on a separate time, I guess a week ago or so. These are called RGB LEDs, so they can literally create any color that you want by passing them R, G, and B values. Okay, so there are all sorts of LEDs, and these LEDs, if you looked at them, they have two legs, and one of the legs is taller than the other one. Let me go back. You can see here, this one, the left leg is clearly bigger than the right leg, okay, to indicate which one is anode, which one is cathode. One leg is longer, and these guys will emit light. So let's discuss that here for you. So this is what I just showed you. Their symbol is like a PN LED, but you have this kind of light rays going out to show that they are emitting light. And as you can see in this diagram, you see that it is going from the long leg to the short leg. So the long leg is the positive leg or anode, the short leg is cathode or the negative leg. So the electricity should go like this. If you have a circuit, okay, it has to go like this. This is the positive side, this is the negative side. And then they will, once this voltage is above their forward voltage, right, or barrier voltage, they start putting different beautiful colors for you. So they are used in indicators, display, optical communications, and so on. And a red LED, which emits light at 660 nanometer, is one of them, but there are all sorts of other LEDs that are out there. Okay, now one thing about their forward voltage is typically quite a bit larger than a standard silicone one. Okay, so you see here the forward voltage of this guy is about 1.345 something. After that is when they start showing their behavior. Okay, and that's one thing. The other thing is this forward voltage that you have to overcome to start emitting light, that depends on the color. So if you have a blue LED or a yellow or red or green, their forward voltages are quite a bit different. So you see that for a red one is about 1.34. For instance, for a green one, it is a little bit more, maybe 1.67. For a blue one, you are passing between 2 to 3 voltage, or around 3, before you can emit any light. So the forward voltage does depend on the frequency of the light. Okay, the bigger the frequency is, you go more toward blue, the bigger the forward voltage. But the more you go toward red, you have a smaller voltage that you need to pass. But all of them are more than 0.5 or 0.6 of typical PN junction diodes. Okay, so this is the characteristic of LEDs. And as you know, for LEDs, you have to connect them to a power source with some resistor, right? So when I showed you that LED, let me show you again. So this is my LED, let's say red LED or whatever. When you want to connect them to this power source, you put a resistor on the way. Okay, you put some resistor on the way. And why would you do that? Because each LED can only allow so much current to pass. So this current that goes through the LED is limited. You don't want the current passing through LEDs to be very, very large. And if you remember in one of my previous videos where I talked about an LED blinking, let's see if I can find it for you. Yeah, this one. You can see that I used a resistor here. Okay, you see that I used a resistor here. You can see it. And the reason is, as I said, these LEDs can only tolerate so much of forward current. So the way that we calculated the amount of resistance, if you look back, was you look at their forward voltage. This is the VF. So this LED had about 2 volts. And then the power that was coming through Arduino was 5 volts. And the current that I can allow to be inside this LED was something about 15 milliamps. you don't want to go more than that. You're going to burn the LED. So when you divide Vs minus Vf divided by this current, you see that the resistors that you needed was 220 ohms. Okay, so the resistor that you need is V minus Vf, or V of source minus Vf, divided by I of the diode, okay, in the forward direction. So this is the I that is recommended for a typical LED. You can look at the manufacturer recommendations and find how much of current is allowed to pass through your LED. So if I go back to my lecture here, so keep that in mind. There is one other thing that I want to talk about, and that is photodiodes. And by the way, the thing I just mentioned, you see that I have added it to my lecture, Vs minus Vf over R. Okay, that is the resistor that you have to have, and typically the current is no more than 20 milliamps. Okay, so look at the Vf and look at your current and decide how much of resistance that you need. Now, photodiodes are the diodes that, when basically you shine light on them, when you put light over them, they create electric current. There is some small leakage current that flows through them. Okay, so you have to shine light on them, then some current will pass through them. These are photodiodes. And if you want to see how they look like this. Okay, so that is a photodiode. They convert light into electric current, and you can see they look like a PN, but the lights are coming in because they receive light, they create current. They are used in light sensors, in fiber optics, in solar panels, and one common chip is BPW34. Okay, and if you look at this surface, you see it's kind of similar to a solar panel here, right? Because they get the light and they create current. So it's obvious if you use them in solar panel or sensors that are looking for light or something, in light sensors. So these are photodiodes. And for a photodiode, again, the current versus voltage, you can see how it is shown here. In the reverse bias, you can see that there is kind of a constant current passing through them. And in the forward bias, the current is kind of going up like exponential function. Okay? Now, how much current will pass through them depends on the intensity of the light. The more light that you pass through them, the more current they are going to basically generate. So you see here is no light. They generate very small current. But as the light is increasing, you can see that the amount of current they generate is basically increasing as well. So this is the behavior of a photodiode. So here are the 5 types of diode that I gone through for you in this video, right? PN, Zener, LEDs, photodiodes, and Shockeys. I mentioned how they look like, what are their symbols, where is it they are used, and one example of their chips and some of their characteristic behaviors. We also looked at the full wave rectifiers and very basic voltage regulators, the Shockley equation, and how to a little bit about doping and the basically what we call the depletion region, and finally forward backward bias and measuring the forward voltage using a multimeter. So hopefully this video was useful to you. You learned some basics and fundamentals about diodes, and I'll see you in the next lecture. Thank you.